All right. So we've been talking about redox reactions, either element or a species gaining or losing an electron in a reaction, right? That's called a redox reaction. When an element is reduced, that means it gains electrons. And when it's oxidized, if a species is oxidized, it means it's losing electrons. Okay? And we now want to be able to look at a chemical reaction like this one here, C8H18 plus O2 coming together to form carbon dioxide and water. This reaction isn't balanced right now. I haven't balanced it, but we don't need to balance it to recognize that simply by looking at the elements here within these compounds, it might not be so easy to identify the oxidation numbers. This is a reaction we've seen before. Do you remember this one, Fred?
Yeah, it's like gasoline or something, right? Octane?
That's right, C8H18, it's octane. This is a redox reaction. This is a redox reaction. But it's not straightforward for us to see where the oxidation is occurring, perhaps, or where the reduction is occurring. To do this, what we need to do is we need to be given tools that will allow us to identify oxidation numbers of elements within compounds. So for another example, here's a compound, CaCO3. All right, what's the oxidation number of the calcium, carbon, and oxygen in calcium carbonate? So here's how we do this. First of all, we're given a list of rules. Now, these rules tell us oxidation numbers for some common scenarios or some common elements. Okay? So if we read through these rules,
Are we gonna have to memorize these rules?
well, as we go through them, you're going to see that most of these rules are rules that you already know. Examples or scenarios where the oxidation number for a given element is already identified. And so these rules are really just here for their order, but you'll see as we go through them, it won't be a big deal.
You didn't answer my question. I feel like we're gonna have to memorize these rules.
You will know enough of these rules that it won't be a constant need for memorization. How's that?
I still don't like the answer, but whatever.
Okay, so here's the first rule. Any free element has an oxidation number of 0. So if it's just an atom of silver, for example, or an elemental molecule, atom of helium, or a hydrogen gas, right? An element by itself, its oxidation number is just 0. And that has to be related to the relationship between the number of protons and electrons it has. Silver, how many protons are in a silver atom?
Silver? Let's see, 47?
Good job, 47 in the silver atom, right? And how many electrons?
Also 47.
That's right, and so the oxidation number there is 0. Helium, 2 protons, 2 electrons, oxidation number is 0. Hydrogen, in this scenario, there's 2 hydrogens, so each one has 1, so there's a total of 2 protons, and a total of 2 electrons. So again, the oxidation number is 0. Any free element by itself, its oxidation number is 0. If it's a monatomic ion like sodium ion is an example of a monatomic ion. The bromide ion, a monatomic ion, right? Oxide ion, monatomic ion. Sulfide ion, monatomic ion. All right? The charge on monatomic ions is the oxidation number. All right? So that's always easy. Therefore, if we look at a compound like calcium carbonate, what's the charge on the calcium in this compound?
That's a +2.
That's right. And so the calcium has a +2 oxidation state, a 2+ oxidation state as well, because it's a simple monatomic ion. That's the second rule. The third one is that fluorine is going to be -1 in its compounds. All right? So fluorine is a -1 in its compounds. Rule 4, group 1A elements, which are the first column here, they're going to be +1, and group 2 is going to be +2. Now those rules are already pretty straightforward, right? Because we already know that when they're in compounds, they're going to be ionic compounds. And the charge on monatomic ions is the oxidation number. So, like I explained before, these rules are things that we've already kind of become aware of, right? Familiar with. Hydrogen is a +1. Oxygen is a -2, right? And then rule 8 is an important rule here. The sum of all the oxidation numbers within an compound add up to the charge on that compound. So here's an example, calcium carbonate. Whatever the oxidation number is by the calciums, and whatever the oxidation is by the carbons, and the contribution by the oxygens, has to add up to what the charge is, and this charge is 0. So in a scenario like this where we have calcium carbonate, we have a rule for calcium. What did we say the oxidation number for the calcium is?
+2.
All right. And if that is the contribution that's contributed by the carbon, oxygen we have a rule for. What's its contribution?
-2.
Okay. Each oxygen has an oxidation state of -2, but there's 3 of them. So that's going to contribute a total of -6. Does that make sense?
Where'd you get the -6?
Each oxygen we said had what oxidation state?
-2.
And there's 3 of them, right?
Yeah.
So -6 is what it's contributing to the overall compound, because the sum of the contributions here have to add up to the charge, which is 0. Okay? So carbon must have what kind of a contribution then?
Oh, you mean like is that going to be a +4?
That's right, +4, because it has to add up to 0. So I can see that the calcium was a +2, the carbon has an oxidation state of +4, and each oxygen has an oxidation state of -2.
I thought it was -6.
-6 is the contribution by all 3 of the oxygens, but each individually have an oxidation state of -2. And that's what you're always going to want to identify, is what's the oxidation state of the individual atoms within a compound. Okay, so if there's a conflict between the 2 rules, then we apply the rule that is higher up before the one that is lower down below. Okay? So that's an important rule to remember as well. Okay, so let's look at these compounds and see if we can identify what the oxidation number for the elements in these compounds is. Iron oxide, we got Fe2O3. This is iron 3 oxide. And the oxygens are a -2. That's the answers right there, right? We can see that we can double check here to make sure that the contribution from the irons plus the contributions from the oxygens should equal 0. Oxygens should be a total of what here?
-6.
And this should be +6 as well, right?
Yeah.
Yeah. So our oxidation numbers are easily identified there because it's just the charge on those monatomic ions, right? All right, sodium carbonate, Na2CO3. Contribution by the sodium plus that of the carbons plus that of the oxygens equals 0. No charge on this thing. So -6, so +2, +4, is that right?
Yeah, okay.
So sodium is a +1, carbon's a +4, and oxygen's a -2. All right, vanadium hydroxide. Vanadium, its contribution, plus the contribution of the oxygen, plus that of the hydrogen, has to equal 0 here. Each oxygen is a -2, right?
Yeah.
And there's 3 of them.
So -6.
And then
the hydrogen's a +3.
All right. And the vanadium here.
Got to be another +3.
All right. Now we really didn't need that because I could see that this was an ionic compound, right? And I could see that each hydroxide is a -1. So this has to have a +3 charge. And the oxygen's going to have -2 and hydrogen's going to have +1. So that's pretty straightforward. How about this one, potassium dichromate?
Potassium's +1.
Very good. Cr2O7. Potassium contributes +1, total of +2. Chromine's contribution, the oxygen's contribution is a minus 14.
Plus 12.
Plus 12 in here.
Yeah. So does that mean chromium is a plus 12?
Well, there's two chromiums. Can you see that? Two chromiums? So each chromium must be a plus 6, so that two of them could have contributed that plus 2, or plus 12. Okay, good. So what's the oxidation number of fluorine in F2O?
Oxygen's minus 2, fluorine's plus 1.
Well, actually, we have a rule for fluorine.
Oh, do we?
Go back and see if we can see it.
Oh, fluorine's a minus 1.
Yeah, so fluorine is a minus 1. If fluorine needs to be a minus 1 here, it means that two of them contribute a minus 2, plus whatever oxygen is, means that oxygen must be a plus 2. Can you see that?
Yeah, I see that.
So the oxidation number for fluorine is minus 1. So the strange scenario is the oxygen. The oxygen is a plus 2 here. All right, what about the phosphorus in phosphorus acid? Phosphorus acid.
Hydrogen's plus 1, oxygen's minus 2. So minus 6 plus 3, so plus 3?
That's right. Very good. Plus 3. Let's tease that out for people who didn't quite follow what you were talking about. H3PO3, the contribution by the hydrogen, plus that of the phosphorus, plus that of the oxygen equals 0. Hydrogen plus 1, 3 of them. Oxygen minus 2, 6 or 3 of those, so 6 of that there. So that makes this phosphorus a plus 3. Okay, good. How about this one?
Well, can you do that one?
You can do that one. Let's see, how can we do this one? H2O2.
Hydrogen's supposed to be plus 1, plus 2, but oxygen's supposed to be minus 2, minus 4. So that doesn't make sense.
The contribution by the hydrogen plus that of the oxygen has to equal 0. Hydrogen's a plus 1, so it's plus 2. Oxygen's a minus 2, so it's a minus 4. Okay, I see what you're saying. So that means if there's a discrepancy in the rules, then we have to go back and find out which one comes first. Which rule comes first? It looks like rule 6 is that hydrogen's a plus 1, and that 7 is that oxygen is a minus 2. So the hydrogen rule takes precedence. See how we knew that?
Because it's higher up in the list?
Yeah. That's right. So that means that the oxygen needs to be flexible, right? And so this is going to be a plus 2. This needs to be a minus 2 here. That means each oxygen is going to be a minus 1. Okay, good. Another thing that we can do with this is we can look at a chemical reaction and know whether or not it's a redox reaction. Because if it's a redox reaction, then some of the oxidation numbers will change from the elements on the left to the elements on the right. Okay? So, for example, if we look at this first reaction here, the oxidation number of this potassium, what is it?
Plus 1.
And in this compound here, what is it?
It's also plus 1. Chlorine there's minus 1, and then on the right it's minus 1. So they didn't change.
That's right. So this process here is not a redox reaction. How about this one here? What's the oxidation number for the copper here?
Plus 2.
Is it?
Oh, is it 0?
That's right. It's just elemental by itself. So copper and sulfur are 0 here. But on the right side of the reaction, you see that now this copper is what?
Plus 2.
That's right. And the sulfide ion minus 2 here. So it went from 0 to a plus 2 and 0 to a minus 2. So this is our redox reaction. Potassium here is a plus 1 over here. Barium is a plus 2 over here. Manganese, a plus 7 here. Also a plus 7 over here, right?
How'd you do that one?
Let's look at the KMNO4. Potassium we said was a +1. Oxygen's contribution here is a -14. The minus sign there. The sum has to equal to 0, so that makes this a plus. Oh, this is a K2, right? No, it's just one. Just one potassium. So plus 14. Oh, not plus 14. That's 2 times 4 is a -8. So that makes that a +7. That's how we got that +7. Okay, good. So B is the redox reaction here. If you go through each of these and check the redox numbers or for all these different elements, you'll find that they're the same. We can also identify the oxidizing agent using the oxidation state for all the different elements. All right. So for example, if we look at the sulfur in H2SO3 and see what it becomes over here on the left, SO4 2-. Here oxygen's a -2. There's a total of -8. Sulfur must be a +4 to have a total charge of -2 there. -4, no, it has to be a +6. +6. Okay, for this one over here, oxygen's a -2. That's a total of -6. Sulfur's contribution, hydrogen's a +2, equals +4 over here. So sulfur went from a +4 to a +6. So that means this was an oxidation. Therefore, this other compound must have oxidized it. And this compound here is the oxidizing agent. See how we did that?
We identified what was oxidized, and then the other one must have been the oxidizing agent?
That's right. You can also look at the compound that's been reduced, and that means that compound must be the oxidizing agent. Okay, here's another scenario. What's the oxidizing agent in this reaction here?
Well, I can see chromium was oxidized.
Very good. Chromium was oxidized. It went from 0 to a plus, what is it here?
Let's see, -4, -12, +6.
Is that right? Cr2O72-, so it's a -2. The contribution by the oxygen is -14, so this is a +12, and that has to divide on 2 chromiums, so each chromium has to be a +6, each oxygen has to be a -2. So it went from 0 to +6. So that's an oxidation, so the oxidizing agent was the MnO4-. Okay. Here's another one. You folks at home, take a second and try to do this one. Did they do it, Fred?
I think so. Can I show you?
Yeah, you can tell me. What's the oxidation? What's being oxidized in this reaction?
The ClO-.
Okay. What was the oxidation number of the ClO- on the left?
It's a -2. It's a +1.
Oxygen is a -2. Total of a -1 is what they're going to get. What we're going to get here. So this is a +1, and the ClO3-, -6, -1 is chloride atom here is a +5. So it went from Cl to the +1 to Cl with a +5. So that is what's being oxidized in this process. I think that we have the wrong answer. This isn't the correct answer. The correct answer is ClO- there. Okay, good. All right, that's a good place to stop. We learned all about redox reactions.